He was a German meteorologist who looked at Earth and who thought that Earth had a situation where the plates fit, or sorry, the continents fit together. And he assembled these lines of evidence that we looked at from the fit of the continents. And I can show you, kind of skip to the end, I can show you a little animation. This is from the UK, so it's centered on the UK, but a little animation of what actually happened when we talk about plate tectonics. This is going from 450 million years ago to today, so I'll just leave it on in the background as we talk. So he assembled this based on the fit of the continents, and then based on the fossil and paleoclimatic evidence in the sedimentary rocks, and then also the igneous and metamorphic rock chemistry, as well as the fabric of these rocks. And he was thwarted by physicists. We talked about Harold Jeffreys. There's also a couple of other physicists who didn't like his theory because he failed to provide a mechanism. So then we talked about all of the things that came later that were seemingly unrelated. These were going on all at the same time in the 1950s and 1960s as we started to get more interested in Earth. And we revisited Wegener's notion of continental drift, which was a failed theory because it failed to provide a mechanism. And we renamed it plate tectonics. And so this is the video of what went on. Go back to the previous one. And I'm going to show you this one more time just because remember that I said that if he had used the continental shelf instead of simply the edges of the continents, he would have got a lot better fit. So his fit was pretty good. But what you can see here is that the lighter colored areas, these are areas of continental shelf. And this will make more sense. Yeah? Can't hear me. Okay. This will make more sense when we look at, better? Yeah, okay, good. This will make more sense when we look at the plates themselves. And so there are places on Earth where the continental shelf, the same thing as the continent, has been drowned by sea level. Sea level is somewhat arbitrary. It rises and falls through time. But the continental shelf, it marks the edge of the continents. And if he had used the continental shelf, he would have got pretty much a perfect fit. So that leads us to plate tectonics, which we ended on last time. I'm going to show you a couple of animations off of this page as well. So plate tectonics describes the motion of the plates through subduction and seafloor spreading. We said that they ride around on the surface of Earth like bumper cars, slamming into each other, pulling past each other, and sliding past each other. And this movement is due to heat inside Earth that is coming out and cooling. And we'll look at this. I showed you this picture, and this picture was just to see that the Earth's surface is quite young relative to the age of Earth, which is 4.6 billion years old. So here's a picture of the actual plates. And this is not something you need to know the plates or memorize the plates. Just understand that there are plates on Earth. And this is one of the places where Wegener kind of went wrong, right? He thought that the continents were plowing through the ocean floor. And an important thing to look at with regards to these plates is that there is continent on the plate, but there's also, in most of these plates, ocean. So for example, we're on the North American plate, all of we except for Los Angeles, and the North American plate actually comes over and continues over. A piece of Japan is on the North American plate. There's a lot of ocean on it, half of the Atlantic. Sometimes the edge of a plate is coincident with a continent, such as the case in the South American plate. The west side of the South American plate is the edge of the continent and the edge of the plate. But you see that the eastern side is the continent plus some of the seafloor. So this is where he went wrong. These are the plates that are moving around. You see also the African plate and the Arabian plate. They were once sort of entire smushed together. We'll look at how Africa's launching Saudi Arabia now, but those are two different plates. The Australian Indian plate has Australia and India. So you get the point. It's not that there are continents that are sliding around. And I'll show you in side view one of these plates.
So we can revisit this notion that there's a core, mantle, and crust, which we talked about the second day of class, but you can also subdivide based on what is solid and what is very thick but gelatinous, capable of slow movement. So in this picture, you see the continental crust. We briefly mentioned volcanic rocks, right? Continental crust is very light. It's light in color, it's light in density. It has more silica in it, talking about the granitic kind of things, and 35 to 70 kilometers thick. And then you grade over into ocean crust, about 5 kilometers thick. It's a lot more dense. It has more metals in it. It's more like the composition of the mantle beneath it. And so then you have this lower part of the lithospheric plate that is actually mantle. This is all mantle here, but we've cooled the upper part of the mantle. And so the lithospheric plate and the crust are two different things. So the lithospheric plate encompasses the crust and the uppermost mantle. And so that's why you can see on this is one plate turned sideways. The gradation between the continental crust and the ocean crust is not germane to the whole lithospheric plate here. Furthermore, right, when Wegener was looking at the edges of the continents, sea level rises and falls through time. So where sea level is right now is a somewhat arbitrary measurement. And so it's not really appropriate to match up one side of a continent with another because of the sea level rising and falling in different widths of the continental shelf. So that's a plate, the lithospheric plate. And beneath the plate is the asthenosphere. Again, it's frequently drawn as very liquid, hot looking like magma. It's almost cool. So what makes the plates move instead of just sitting there? Why are they broken up and sliding around? Well, there are three mechanisms. These last two are very, very much downplayed these days. It was thought that they played more of a role than they actually do, but I'll still mention them. The biggest, oh, by the way, if you are looking for these slides, they were named something that had them further down on Canvas, but they are on now. They're called EG2-3, plate tectonics. So if you're looking for the slides, they are there. They were there as of yesterday afternoon. So convection cells are the big mechanism by which these plates slide around. So we'll look first at convection cells, and then I'll briefly mention the other two. Okay. So how many of you have made a convection cell in your kitchen? One person? Two? How many of you have boiled water for pasta? Okay, most of you. Then you've made a convection cell. Convection cells, we will look at them again when we look up in the atmosphere, but a convection cell happens in a fluid as a result of a temperature differential. So think about boiling water in your apartment or your dorm room for pasta, for whatever it is you're eating. You take a pan, you put it on the stove, and you turn on the heat source. What that sets up is a gradient. It's filled with water, right, this fluid. What that sets up is a gradient, which is what you can see here. At the bottom of the pan, the water is in contact, through the pan, right, with a hot temperature. And so the molecules of the water at the bottom start vibrating like crazy. That makes the mass of water at the bottom less dense, and it rises up the side of the pan. This works especially well if you apply the heat to the edges, like a gas stove. But it rises up the side of a pan where it comes in contact with, here's my sort of fake animation, where it comes in contact with the cool air in your apartment, in your dorm. And it's got to get out of the way of the stuff that's constantly coming behind it. So it moves along the surface of the pan, but now it's in contact with the relatively cool atmosphere in your house. And so the molecules start vibrating less rapidly. That means it's cooled and it's more dense. So you have an unstable situation, right? You have less dense stuff on top of more dense stuff. That's not how things work. So the stuff is coming along the side of the pan through the surface. It hits in the middle, more or less, and will sink down because it's cold and it's more dense than the stuff coming up behind it. And then once it gets to the bottom, the same thing happens all over again, right? You have this sinking down, gets to the bottom, where it's now again in contact with the heat source, and the molecules start vibrating more rapidly, rises up again. And you have these convection cells. You can look at animations online of convection cells. You can put dye in a pan and do it yourself, or a coffee ground or something like that. Or next time you're making pasta, any long pasta, you can just don't stir it like the directions say. And at the end of the cooking, you'll see that it is tracing the path of the convection cell in the pan. So this simple mechanism by which the water is moving around in the pan goes on beneath your feet in the asthenosphere. And these are some of the convection cells and what happens as a result of the convecting beneath us. So the stuff down here, the outer core, inner core, very, very hot. So the molecules in the asthenosphere, right, start vibrating rapidly, move up. And so that's right here. They move up. They get to the surface. I'll show you a couple of animations like this. And then they have to move along to get out of the way of the stuff that's coming beneath it. And that is seafloor spreading. That is the fact that at that spot, new seafloor is being created. Magma is coming up, cooling, becoming lava, cooling, and moving along. So you're creating new seafloor. That was one of the mechanisms that we talked about with regards to seafloor spreading. Those volcanoes are laying down new seafloor. And then eventually, as you see here, the convection cells will come together and they dive down to warm back up. This is a boundary that we'll look at called the convergent boundary. The plates come together and we'll look at what happens based on what kind of crust is there, what kind of lithosphere is there. Sometimes it crunches upwards and makes mountains. Sometimes one plate dives down under the other one and that will melt and be recycled in the mantle. And sometimes where the convection cells are adjacent, then you can cause the plates to slide past each other. So those are the convection cells, and I'll talk about those boundaries in a minute. But that's the mechanism by which the plates are moving around. Also, again, this is thought to be more important at one point, and it's downplayed these days, but this notion of hot plumes, which we'll look at a lot when we talk about volcanoes. Superheated plumes of magma coming from either the inner core, the outer core or inner mantle, burning up through the mesosphere, the asthenosphere, and eventually, as in the case of Hawaii, as in the case of Iceland, burning through the lithospheric plate and creating land or an underwater volcano. So it was thought that that played a role in plate tectonics as well, shifting the plates around. And then this, again, I don't want to put too much on this because it is really downplayed as a mechanism, but this is really kind of the same thing as convection cells, except now we're talking about the solid part at the top of Earth rather than underneath the liquid part that's flowing. So what happens is, as this convection cell is going on right here, you have a divergent boundary here, which we'll look at, and then you have the convection cell coming down here, and because of this plate being solid, it gets pulled and sucked down by the convection cell. So that's slab pull. It gets pulled down into the asthenosphere. Again, very similar to convection, but now we're talking about the part that is solid. And at the mid-ocean ridge, the stuff that is cooled slides away, and that's called ridge push, by the stuff that's coming up and solidifying behind it. So you're pushing the plate apart at the ridge, and you're pulling it, sucking it under at the subduction zone. Now, you haven't named these yet, but I'll show you these in a minute. So those are the mechanisms by which the plates move. And now we can look at the types of plate boundaries. There are three types of plate boundaries. I kind of started saying things about them now. But the plate boundaries are convergent, and I have a slide on each one of these, so you don't have to try to write them down if you don't want to. Convergent, divergent, and transform. So let's look at convergent boundaries first. You know what the word converge means, right? If you converge in this room at 10 a.m., it's to come together, right? So the plates are coming together. It's a convergent boundary. And the rule with the convergent boundary is that continental crust is very thick in thickness. It is light because it's got a lot more silica in it. And so it will not subduct, subduction zone. It will not dive down under the other plate. If you have an ocean plate, again, it's very thin and it's dense. And when you have a subduction zone, an ocean plate will dive down. So let's look at these boundaries. The top picture here, you have two oceanic plates coming together because if you're looking beneath it, you have convection
better? Yeah, okay. So one plate will dive down under the other one. And you see what happens. It can only go down so low before it melts. And when it melts, that material will stream up through the overlying material, and it will burn through the other plate, and you make an island arc, a chain of islands. So this ocean plate dove under this ocean plate. It melts, it sends fingers of magma streaming up through, and you get a little chain of islands on the seafloor because of that convergent boundary. In the center part, you have a situation where a continent and ocean crust are crashing into each other, lithosphere, and the ocean, again, will dive down underneath. Same thing. This is what's going on in the Pacific Northwest. The volcanoes we'll look at there. Mount St. Helens, Mount Shasta, Mount Rainier, Mount Hood. The plate dives down, and it will melt, and it will send fingers of magma going up through the ocean, the continental plate, and you have a chain of volcanoes on land. And that's that middle kind of igneous rock where you have ocean stuff mixing with continental stuff, and you make andesitic kind of material. Here you have a situation where continent hits continent. In this case, again, neither one is going to seed, so they smash together and they crunch upwards. This is where you have huge metamorphic zones at the base of these mountains. So they crunch upwards. And you see if you play the tape recorder backwards, as we geologists talk about, what is this? What's the green stuff here? Ocean, exactly, ocean. So what happened if you could be looking at this straight down, there were two continents and there was ocean, and you closed an ocean basin. The ocean crust dove down and it was melting and sending fingers of magma up, but then it hit a continent, got stuck, and started crunching upwards. This is how you make big mountains. Mount Everest, the Himalayan mountains, were created by continent-continent conversion when India slammed into Asia, crunched upwards. So this is a convergent boundary. The plates converge, and you see what happens at these different boundaries, or this boundary based on the different type of crust. The next type of boundary is a divergent boundary. If you diverge, you go apart from each other, right? So a divergent boundary is where the plates are coming apart. Magma is welling up from the mantle through the asthenosphere. It is coming out like a conveyor belt, making new crust, and you're creating new seafloor. And so on the ocean, this would manifest as continents moving farther apart from each other if there are continents on that plate. Or this happens on land, and it's called a rift zone. I'll show you an animation of this. So you have convection cells going like this. This was once an entire continent, but it's straddling two convection cells, and so it gets pulled apart. Again, we'll see how Africa and Saudi Arabia were once together, and the Red Sea is growing because there is rifting there. The East African Rift Zone, which we'll look at. The continent is getting stretched thin, and you'll expect seawater to invade in that area. Interestingly, when we talk about earthquakes, our second natural disaster, there was a swarm of thousands of earthquakes, roughly coincident with the Mississippi River back in the 1800s. And it is thought, this is complicated, but it is thought that there was a rift zone that started, convection cells started to pull North America apart, but then it stopped. And there were a lot of earthquakes. The Mississippi River reversed its flow temporarily. The shocks were so big down in New Madrid, we'll look at this earthquake, that it rang the church bells in Boston. So they were quite significant earthquakes, and a lot of them. So that is a divergent boundary. You're splitting things in two. Another interesting thing about divergent boundaries is you have a lot of hot material mixing with seawater, and you can get these hydrothermal vents with bizarre organisms these are called tube worms, 2 to 3 feet long. You have whole colonies of them. This is an arthropod. You see that's a man's hand, so it's about the size of a small human baby. You have black smokers and white smokers. It looks like smoke, but it's water that's issuing forth out of a hydrothermal vent that has all sorts of impurities or all sorts of minerals dissolved in it. So interesting things happen at divergent boundaries when you have hydrothermal vents. There's another picture of a divergent boundary. in a couple of sense. You have the East African Rift Zone, and then you have here the Arabian Peninsula is being pulled away by mantle convection from Africa. And then the last type of boundary is called a transform boundary. Again, they slide past each other. So you all know, I'm sure, of the San Andreas Fault. This is a complicated system. I'm talking about this in a very simplified way in an intro class. But what's happening here, this is a neat fault because actually all three types of boundaries are represented here. In the center part of this, you have the San Andreas Fault where Los Angeles is actually on the Pacific Plate. Los Angeles is creeping northward. San Francisco is creeping southward. Eventually, they're going to be like the Twin Cities, right next to each other. And 50 million years from now, we're going to launch Los Angeles off into the ocean as an island. We won't be here, but that's the situation because they're sliding past each other. In the south, Baja California, the Gulf of California, that's actually a divergent boundary. You have really kind of neat stuff going on here. You see that this coastline matches up with this coastline because they were once together. And then because of a little plate up there called the Juan de Fuca plate, those teeth signify a convergent boundary. The convergent boundary, Juan de Fuca plate, is diving down underneath the North American plate. It's melting and it's sending fingers of magma up through the North American plate. And again, that's the Cascade Range Mountains. So you have all three plate boundaries represented here. And I'll show you a couple, I don't know if you need this, but I'll show you a couple of animations. They're simple cartoon diagram animations, but they might be helpful in looking at this. So we will look first at basic plate boundaries. Just going to put these out in order. Here's an animation of a divergent boundary. You have continent, continent. The convection cells are going like this, and you're creating new seafloor. We talked about the mechanism, or the things that we learned at the supported plate tectonics. There's seafloor spreading. If you're thinking of this as North America, that is Europe, there's that mid-ocean ridge, and new seafloors being created. The opposite happens at a convergent boundary. This ocean basin, as you can see, is being closed. You have mountains being created, and eventually, if you're looking at India and China, what happens is this one slams into that one, and the continents will crunch upwards. And then we have transform boundary, slide past each other. This is where we say earthquakes happen, but earthquakes, big earthquakes, can happen at convergent boundaries. So that is plate boundaries. This is just a blow up of what happens at that divergent boundary. Magma's welling up and is making new seafloor. Remember that we have these geomagnetic reversals, right? And so the magnetite crystals in here are going to always be pointing to where magnetic north is located. So that is formation of ocean crust. Here's subduction. We looked at convergent boundaries. This plate is subducting. You're making volcanoes, and you scraped off all of the seafloor sediments that we talked about last time. It's called an accretionary prism. Transform faulting. We don't need to see this, I don't think. Here's process of rifting, breaking apart. So again, underneath here is a divergent boundary. The mantle convection is going in this direction. You're stretching the lithospheric plate thin. This was one continent. And eventually you stretch the lithospheric plate so thin that it's going to break in two, and you're going to have an ocean basin created rather than closed. So here's the point at which the ocean basin starts. Now you have two separate plates created out of one. And that was what almost happened in the United States. And that is it. I think there was a geomagnetic reversal picture, but this is one that's from yesterday. This is putting together the geomagnetic reversals with the seafloor spreading. and the paleomagnetism, so stripes. What's going on here is, again, conceptually you can think of Earth as having a big bar magnet in it, and occasionally the North Pole is magnetic north, and then because of these slow convection currents in the mantle, the core will actually stop, and it will start spinning again, but it spins in the opposite direction. That's what's responsible for changing the magnetic orientation of Earth. Here's North America, here's Europe. You see that the magma's coming out, so now you have these convection cells going like this, creating that chain of volcanoes. The magnetite crystals that are in that basalt are tracking what the magnetic field of Earth is doing. As long as magnetic north is in the north, you have gray stuff being created. When it's in the south, you have green stuff being created. And then you can match up the stripes along the seafloor and play the tape recorder back again, as we geologists say, to a point where Europe and North America were touching. So, the bottom line with regards to plate tectonics and our poor friend Alfred Wegener is that he was right. He was absolutely right in his notion that the plates were once together, or the continents were once together in a certain way, and they drifted apart. Though he had a couple of details wrong. For 1910s, he did a great job. 50 million years ago, the most active places on Earth right now, North America, again, is going to launch Los Angeles out into the Pacific Ocean. Africa is going to continue to launch the Arabian plate, Saudi Arabia and the countries there. And Australia, this is the fastest place where plate tectonics is going on. Australia is moving northward. It's on a crash course towards the Philippine Islands. It's going to accrete the Philippine Islands and continue to cruise northward. So that's what's going on on the world or on the planet with regards to tectonics in a fast way. And that's it for